Alright, so we're continuing. This is our day 2 on vectors, and we're going to start with a vector operation called the dot product. So on your purple sheet, you will see that you have dot product written here. Okay, so you don't have to memorize this formula, but you do have to understand it. So what the dot product says, if we have two vectors, if we have vector u with the components u1, u2, so reminder, u1 is your horizontal component, u2 is your vertical component, and we have another vector, vector v, and it is v1, v2, again, horizontal and vertical. Then there's this operation that we do called the dot product. And it looks like this, vector u dot vector v. So it's not the same as multiplication, right? It's a special operation. And it goes like this. Take the two horizontal components and multiply them together. So u1 times v1. And then add that with the two vertical components multiplied together. u2 times v2. So that's how we calculate a dot product. So when you see this dot with vectors, you say dot. Don't say multiply, don't say times, because it's not exactly the same thing as traditional multiplication. Alright, so let's jump into an example. So if I have vector u with the components 3, 6, and I have vector v with the components 10, -4. And then if I'm going to perform the dot product of u dot v, here's how that process is going to go. Take the horizontal component, 3, multiply it by the other horizontal component, which is 10. Then add the vertical component of 6 multiplied by the other vertical component, -4. Three times 10 gives us 30. 6 times -4 gives us -24. We add that together, we get 6. So that's an interesting thing about the dot product. You take a vector, you perform the dot product with another vector, your answer doesn't come out as a vector. Your answer just comes out as a number. Now, you can also do a dot product with a vector and its own self. So, take vector u and give this a try. U dot u. So did you get 45? Yes? So there's a relationship between a vector being dot product with itself and the magnitude. So remember, last time we studied magnitude. So the magnitude of u is the square root of x squared plus y squared. Remember, that comes from our Pythagorean theorem. So do you see that this is x squared, 3 times 3, and this is y squared? So vector u dot vector u is equal to the magnitude squared. Because this would be 9 plus 36. The magnitude would be the square root of 45, and u dot u is 45. So there's a relationship between dot products and magnitudes. So the other part that we need to do with dot products is just to be able to do them if your vector is written in linear combination form instead of component form. So hopefully you will see that it's not any different. But if I have vector u and I have it written out as 6i plus 4j, and then vector v is written as negative 3i minus 5j, and we want to be able to find u dot v. So if you want to write these into component form, you can, or you can just do it the same way, just looking at it. But remember, this is called linear combination form. And if I rewrite this in component form, it's just saying that my component is horizontal is 6 and vertical is 4. This one is just saying negative 3 for horizontal and negative 5 for vertical. So again, it's just being able to recognize the different formats. So when we do u dot v, we should come out with 6 times negative 3 and 4 times negative 5. And so that's going to come out to be negative 38. Okay? So you need to be able to perform a dot product, whether it's written in linear combination form or component form. Just be used to your different formats. All right. The next thing is, what if we put the dot product together with some of our other operations? So let's say vector u is equal to 2, 5. And vector v is equal to 4, 3. And vector w is equal to negative 1, 6. And then we want to take 3 times vector u, and we want to do the dot product with vector v added with vector w. So this is just a combination of things we learned last block along with the dot product. So I'm going to start with doing this scalar multiplication. So remember, if I want to take vector u and multiply it by 3, it's very similar to distributing. I do 3 times 2 and 3 times 5. Right? So vector 3 times vector u would come out to be 6, 15. Alright, if I want to add vector v and vector w, the rule for that is add your two horizontals. So 4 plus negative 1 is 3. And then add your verticals. So 3 plus 6 is 9. So I multiplied vector u by 3. I added vector v and w together, because that was in parentheses. I got these two resultant vectors. Now I'm going to perform the dot product with these two. So now that's going to be 6 times 3 plus 15 times 9. And what did you get for that? 153. Excellent. All right. The angle between two vectors. So, the formula for this is on your purple sheet, but it's not labeled by what it is. So on your purple sheet here, this formula with cosine theta, right next to it, write angle between two vectors. That's what this is a formula for. Alright, so let's start with vector u being equal to 6, 2, and vector v being equal to negative 4, 3. Alright, so the first thing we want to do is we want to sketch these two vectors and see what is it that we're even talking about here. I'm going to sketch a little coordinate plane. Vector u has a horizontal component of 6 and a vertical component of 2. So that's vector u going off in that direction. Then vector v has a horizontal component of negative 4. And a vertical component of 3. So there's vector v. And so when I am looking at the angle between two vectors, that means we're looking for this angle here. We're going to label our angle with the variable theta. So that's the thing that we're trying to find. That's what we want to know. Now, there is a way to prove this formula. This formula actually comes from the law of cosines. So we know we can find, think about the law of cosines. We know how long these two vectors are, right? Because we can find their magnitude. And then you can use the law of cosines to find your missing angle here. And you can go through a whole proof. But the result is this formula. We're not going to go through the whole proof, but cosine of theta is going to equal vector u's dot product with vector v divided by the magnitude of vector u multiplied by the magnitude of vector v. So before we even start, let's look at our picture. About how big do you think theta is? Is it less than 180? More than 40? More than 80? More than 90? Somewhere between 90 and 180? Right? Sometimes it's good to just write ideas like that down. Math makes sense. Here's a picture. This is an angle. I'm finding an angle. The angle that I'm looking for is obviously, right, between 90 and 180. If I come over here and do all these calculations and I get an answer that's not between 90 and 180, it doesn't make sense. You always want to go back to, does my answer make sense? Alright, so now let's plug things in. Let's start with our numerator. Our numerator is the dot product that we just learned. So, our numerator is going to be 6 times negative 4 plus 2 times 3. Bring down this cosine theta. Alright, on our denominator, we have the magnitude of u. Remember, your magnitude comes from your Pythagorean theorem. So it's the square root. So if I'm looking over here at vector u, remember, here's my right triangle. So this leg is 6 and this leg is 2. So it's the square root of 6 squared plus 2 squared. And then I'm going to multiply that by the magnitude of vector v. So again, vector v is the hypotenuse of a right triangle. And so that's negative 4 squared plus 3 squared. So I'm going to bring down cosine theta. Alright, we multiply this, put it all in your calculator, whichever you like. We're going to come out to negative 18. We're going to plug this in. It's going to come out to square root of 40. Now this one's going to be the square root of 25. And what is the square root of 25? 5. So I'm just going to go ahead and put times 5. Now, at this stage, we could simplify, right? And if square root of 40 was our final answer, we would 100% want to simplify. But to be honest, we don't have to simplify. Once I get everything plugged in, I'm looking for theta. So I need to do an inverse cosine on both sides. So inverse cosine and cosine work together to undo each other, and theta is by itself. And once I get theta by itself, I'm ready to put the other information into my calculator. But let's talk about that. Remember, this fraction bar, this vinculum, is a division sign, but it's also a grouping symbol. So if I type this part into a calculator, I need to do negative 18 divided by parentheses square root of 40 times 5. Because I need to insert parentheses for the grouping symbol of the vinculum. Now, the other way is to just have your calculator put it in fraction form. So let's look at both ways. So on a calculator, I can type in second cosine, and I can do negative 18 divided by parentheses square root 40 times 5. And then I need to close my other parentheses for the end of the inverse cosine. And I've got an angle measurement. Alright. Suppose you're one of those people and you're like, yeah, Miss Collier, I'm always forgetting those parentheses. Well, you can do second cosine, and you can have your calculator put it in fraction form for you. And there's two ways to do it. One is to press the alpha with the variable key, and you see up pops your fraction. Another way is to press alpha with y equals, and then choice 1, and up pops a fraction. Okay. So again, alpha variable button or alpha y equals. You may be used to one or the other already, but if you didn't know that, there you go. So my numerator is negative 18. In my denominator, I have square root of 40 times 5. Make sure you use your arrow key because you don't want your 5 under your square root sign. Alright, then you have to come over here and close your parentheses. And there's your angle measure.
Are you able to plug in the whole thing, like where it's negative 18 over square root 6 plus?
You could. Then you got to be really careful with your parentheses, though, because and where you end your square roots and everything. So to me, you're more likely to make a mistake with your buttons than with your math. But yes, you could take the inverse cosine way up here before you've even done any of the adding. Alright, so we got, if I round to the tenths place, 124.7 degrees. Does this answer make sense with our picture? Yeah. 124, little more than 90. Okay? Math makes sense. Always ask yourself, does this answer make sense?